The other type of induction problem that we see is inequalities, proving inequalities rather than equations. So we're just a simple little one here. 2 to the power of n is always going to be greater than n squared. However, the first time that will happen will be when n is
5.
5. Thank you. That would be the first number bigger than 4. Well done. Because, of course, 2 to the power of 4 is
16.
And 4 squared is
16.
And 16 is not
Greater than 16.
There you go. So in this case, step 1 is going to be proof for n is 5. N is 5. And 2 to the power of 5 is
32.
Seeing you're on a roll there. 32. 5 squared is,
25.
and 32 is bigger than last time I checked. It does work for the first case. Now, going to assume it's true for n equals k, where k is an integer greater than 4. In this case, it is important that I put k is greater than 4, because that also is part of the assumption. So in a way, there's actually 2 assumptions I'm making. I'm assuming 2 to the power of k is greater than k squared, but the other assumption is in there, which is that k is greater than 4. And we're going to prove 2 to the power of k plus 1 is greater than or equal to, so not equal to, just greater than k plus 1 squared. There's different ways of proving this. Some people like to move everything to the left-hand side, show it's always positive. I'm just going to start with an algebraic statement of 2 to the power of k plus 1 and hopefully show it is indeed always greater than k plus 1 squared. Now my assumption was 2 to the power of k. So how do I get that in there? Well, 2 to the power of k is 2 times 2 to the power of k. So therefore that is going to be bigger than 2k squared. Alright, well remember I'm trying to get to k plus 1 squared. Now k plus 1 squared is k squared plus 2k plus 1. So I don't want 2k squared, I just want 1k squared. So I'm going to break that up and make that k squared plus k squared. But the second k squared I'm going to say is k times k. But k, I've assumed, is greater than 4. So I could say that's greater than k squared plus 4k. Because again, remember, the assumption was not only that 2 to the power of k was greater than k squared, the other part of the assumption was k is greater than 4. I don't want 4k, I only want 2k. So I'm going to rewrite that as k squared plus 2k plus 2k. But that second 2k, I'm going to say, well, that's greater than 8, because k is greater than 4. Now, I don't want k squared plus 2k plus 8. I want k squared plus 2k plus 1. However, 8 is bigger than 1. So therefore, k squared plus 2k plus 8 is greater than k squared plus 2k plus 1. So now reading down, I've got 2 to the power of k plus 1 is greater than k squared plus 2k plus 1, which is, of course, k plus 1 squared. So there I've proven it. 2k plus 1 is always greater than k plus 1 squared. Hence the result is true for k plus 1 if it's also true for k. My conclusion will be a little bit different because the first case was n equals 5, so therefore true for greater than 4 by induction. So inequalities are a little bit different because unlike equations where whatever you do to one side you do to the other, I don't have to do that here. Because I'm dealing with greater than, I can subtract 7 from the right-hand side. I don't need to subtract it from the left-hand side. Because if I'm saying it's greater than it, well, if I subtract, it's still greater than it. I can subtract anything I like. And it's still going to be a true statement. So you can have a lot of fun playing with those. Okay. Well, there's a handful of inequality ones to do from 6n.